Today, I'd like to talk about how to extend the idea of a chain rule to functions of more than one variables. I say chain rules here because depending on the context, there may be more than one of them. I want to think about something from statistics and probability. I'm going to imagine that I have a bag of marbles. There are 5 green ones and 7 red ones. I'm going to reach into the bag, grab a marble, and throw it away without looking at it. Then I'm going to reach in and pull a second marble out, and I'd like to know the probability that that second marble is green. To start with, I have 12 marbles and 7 of them are red. The probability that the first marble is red is 7/12. The probability that the first marble is green is 5/12. Let's investigate what happens under various circumstances. Suppose that the first marble was red. I now have only 11 marbles left and only 6 red ones. If the first marble was red, though, I still have all 5 of the green ones that I started with. So if the first marble was red, the probability that the second one is red is 6/11, and given that the first marble was red, the probability that the second marble is green is 5/11. But we're not done yet. There's another way I could get a green marble on the second draw. If the first marble was green, then I now have only 4 green marbles left and still have all 7 of the original. So the probability that if the first marble was green, then the second one is green will be 4 divided by 11. If the first marble is green, given that piece of information, then the probability that the second marble is red is 7/11. The chain of events, first marble red, second marble green, first marble green, second marble green, are mutually exclusive in the sense that if one of those things happens, then the other one does not. This means to get the probability I end up with a green marble on the second draw can be figured out by finding the probability that I take this pathway through my diagram plus the probability that I take that pathway. Even though I didn't observe what color the first marble is, regardless, the probability of the second marble being green is 7/12 times 5/11 plus 5/12 times 4/11. Hopefully everybody remembers doing something like this in a probability or statistics problem at some point. I want to think about a situation in which I've got a function f of x and y that's either defined for the entire xy plane or some chunk of it that I'm interested in. I want to think about traveling along some pathway in this two-dimensional space. I could think of this as being the graph of some vector-valued function in 2 dimensions, or I could just think of having formulas for the x and y coordinate in terms of some other variable that I'll call t. As I travel along this curve, I encounter various points in the plane. Each one of those points has a function value to go with it. But I'm not looking at just any old points now. I'm only looking at points that are on the graph that I've drawn in. If I didn't know that I was on a certain path, I would just write my function values as f of x and y. But if I do know that x and y depend on t, I might as well write that in. As a result, f is at the basic level a function of t. I want to think about starting at some t value on this curve, t equal t0, and traveling out to the place where t is delta t more than where we started off. Likewise, at time t equals t0 plus delta t, I can think of having an x which depends on the t value and y which depends on the t value. So I have two different descriptions for what's going on. One of them is in terms of the t value. The other is in terms of the usual xy coordinates. Looking at the beginning to end of my little diagram here, there'll be a change in x, which I'll call delta x. There'll be a change in y that I call delta y. Obviously, this depends on the details of these formulas, what t0 is, and what delta t is. As long as x and y are nice functions of t, though, if delta t goes to 0, then so does delta x, and so does delta y. I'm going to need to know that in a minute. If I assume that function f is differentiable, though, I do know something. I know that delta z is dz plus epsilon 1 delta x plus epsilon 2 delta y, and epsilon 1 and epsilon 2 both tend to 0, as delta x and delta y tend to 0. And because of the comment that we just made a moment ago, epsilon 1 and epsilon 2 will tend to 0 when delta t tends to 0 as well. I'm going to take that preceding formula and divide both sides of it by delta t. Now I'm going to take the limit as delta t tends to 0. This will be dz dt, the instantaneous rate of change of the function value in terms of t. This doesn't depend on delta t. Assuming my path is smooth, this limit is dx dt. That one will be dy dt, dx dt, dy dt. And remember, as delta t tends to 0, delta x and delta y tend to 0, which makes epsilon 1 and epsilon 2 tend to 0. So in these last two terms, the limit of this one is going to be 0 times dx dt. The limit of that one is going to be 0 times dy dt, and those terms can now be ignored. People will sometimes omit the indicators that tell me where I'm evaluating these things at, with the understanding that the person reading and using these formulas understand what we mean. So I'm going to write this down, but I'll leave that out, and that out, and that, and that. This is the first of several versions of the chain rule that we'll look at. If f has a formula that defines it explicitly in terms of x and y are functions of some other variable t, then the derivative with respect to that variable t of the function value is given by this formula. Now, this will be useful as is, and there are certain implications that will come with it that we'll explore in a little while. You may be wondering what this has to do with the red and green marble problem. So let's draw a diagram that indicates the dependencies of these various quantities on each other. Function f in the situation we're thinking about is some expression involving x's and y's. But in the current situation, we're also thinking of x and y both being functions of some parameter t, often thought of as the time. This resembles the probability diagram that we started off talking about. Instead of writing probabilities down on the various edges, I'm going to write derivatives down instead. The derivative of the thing above with respect to the thing below. If the thing above depends on more than one thing, I'll use the partial derivative symbol, and if it uses only one variable, then I'll use the regular d symbol. F depends on two things, x and y, so I use the partial derivative symbol. On the other hand, x only depends on t, and y only depends on t. If I think of changing the t number, there are two completely independent ways in which this can cause a change in the function value. Changing t by an amount delta t will change x by an amount roughly dx dt times dt, but also changing t will change y. So change t changes x changes f, change t changes y changes f in a different way. If I pretend that these are probabilities in my probability diagram, start at f, partial of f with respect to x times dx dt from this branch, start at the top again, partial of f with respect to y times dy dt from that mutually exclusive branch, add the two contributions together, and if you'll look back at what we just did a moment ago, this is the rate of change of function f with respect to variable t. Now, one thought is that I could just substitute x equals t squared plus 2 and y equal 3t minus 1 into this formula, and then do the usual calculation that you would do from Calc 1. That will give you the correct answer, but it's missing the point. This chain rule thing is going to tell us things later that we are currently not able to figure out easily. So resist the urge to turn this into a Calculus 1 problem. At the place on the path where t is 0, x is going to be 0 squared plus 2, x will be 2, and y will be 3 times 0 minus 1, y is negative 1. This is the xy coordinates of the point that go with t equals 0. The partial derivative of f with respect to x is 2xy cubed, and partial of f with respect to y is 3x squared y squared. I have to evaluate these two partial derivatives at the point that I'm interested in. The point of the graph where t is 0 has x equal 2 and y equal negative 1. At the point of interest, the partial of f with respect to x is negative 4, while partial of f with respect to y is 12. To use my chain rule formula, I also need to know the values of dx dt and dy dt when t is 0. X is t squared plus 2, so dx dt is 2 times t. Y is 3 times t minus 1, so dy dt is always equal to 3. At t equals 0, dx dt is 2 times 0, and dy dt is always 3. We now know this number, that one, and we'll be able to calculate the rate of change of the function along this curve at the point that we're interested in. In the situation that we find ourselves, the function is getting bigger at a rate of 36 units of function value per unit of t right at the point of interest. I'm going to make one more comment and then we'll continue talking about this issue in the next video. I want to write out my formula for the total rate of change of f with respect to t, except I want to write it using rather odd-looking notation. Partial of f with respect to x is in blue. The partial of f with respect to y is in blue. These are pieces of information that have only to do with what the function is at the point of interest. Dx dt and dy dt have nothing to do whatsoever with f. They indicate the rate of change of the x-coordinate and y-coordinate with respect to t along the curve that I'm traveling on at the point of interest. This is very interesting to me. This says I've got a blue piece of information times an orange piece. I have another blue piece of information plus an orange piece, and then I'm going to add those together. It's been a long time since we thought about this, but this reminds me of something. If I have a blue vector, 3i plus 2j, and an orange vector, 4i plus 7j, and form the dot product, it's the first piece of blue information times the first piece of orange information, plus the second piece of blue times the second piece of orange. This chain rule that we've developed for functions of two variables, each one of which is a function of a third variable t, is kind of, sort of, a dot product of two vectors. In the next video, we'll explore some more ideas concerning these chain rules, and in particular, we'll begin to see that our old friends the vectors are going to reappear in the picture once again. Until then, I hope everybody's having a good day, and I'll talk to you again soon.